underpinned by a drawing, which I'll repeat here. The cross-section has of the fuselage has dimensions dy and dx, amounting to a cross-sectional area A. The fuselage length is L. The two wings together are of span S, swept length LW, and thickness T. And to make a drawing, meaning first you have to predict it before you make it, you need proportions. I made the point that the drawing speaks to you not with size, such as millimeters or centimeters, but with relative sizes called proportions or aspect ratios. So the aspect is represented by the slenderness, which is the ratio of fuselage length to transversal dimension of the fuselage, the shape of the cross-section, and then a few other things such as the wingspan relative to the fuselage length, and then the aspect ratio of this so-called wing profile, namely T over LW, and then another aspect ratio of the wing seen from above, namely LW over S. So altogether, 5 degrees of freedom. So we said goodbye at about this stage last time. The mathematical apparatus started with, by the way, I made the point that everything that flies, let's say intelligently, after seeking access, is a body that operates at a balance between the effort to lift itself and then the effort to overcome the ambient as the body falls forward. And in other words, the sum of the two efforts is of the same order of magnitude as as one of those two efforts. And then for that reason, we focus on the, analytically that is, on the effort to overcome drag. So the drag felt by this body in the face of a wind approaching with the speed of the body, which is called capital V, is equal to, and here's the frontal area, meaning for the stagnation pressure on the face, and then a friction coefficient, and then wetted perimeter times L. The wetted perimeter is this. I wouldn't say wetted because the wind is not necessarily full of water droplets. In any case, that's the contribution made by the fuselage. And then plus TS, that is the same sort of thinking with regard to this body, the wing. So TS is the frontal area, and then for the wing, the friction coefficient SLW, and that's for the wing, the wings together. And this is equation number 4. I will refer to these equations by numbers. They are numbered this way in the PDF that I distributed. Continuing. We had equation number 6, which has to do with the mechanical strength. If you look at the body of weight mg is connected to the wing, and the wing is lifted by its design, as it goes through the air, the wing is starting not to hydroplane, but to airplane. And then you've seen this when your airplane takes off, the wing curls up upward. Do you observe this? Yeah, pay attention. Get a seat right there on seat A, just close to the window. But don't go through the window to ride on the wing. Okay, that's not too intelligent. And so this wing is bent upward by the lift. The lift is proportional to this mg, as you'll see very soon. We have the wingspan S, and then the thickness T, of course. And the bending moment that is due to these lifting little arrows is mgs. In the armpit, because now we're talking about the equilibrium of the wing, in the armpit, there is tension called sigma, or S if you want, SMA, and then compression, SMA, with their own couple, meaning bending moment. So SMA is integrated over the cross-sectional area, which is TS, not TS, TLW. TLW, that's the cross-sectional area of this wing. And then the couple, which the arm of this couple, which is T. And this is the same as MGS. And this equation will be equation number 7. Before it, the equation that signifies, meaning goes with this particular drawing, is equation 6, which says that 1/2 rho A, this is the the lifting force, meaning the integral of these arrows, rho A v squared. There's a lift coefficient you can fish out of a aerodynamics book, which is a constant of order 1. And then SLW, this has to be, meaning this is the vertical force balance, force down, force up, and then mg. So that is equation number 6. So we have several equations that I'm going to highlight this way. So 4, 5, and then 6, and 7. The next moves are relatively simple. You know from previous problem solving that the cross section that will well, before I go there, let me tell you this story from from elementary school. So the teacher asked my benchmate to extract the square root of the number 16. And my benchmate with my neighbor said, dear teacher, it would be easier to extract the round root of, because he was thinking of a carrot. Yeah. Pulling carrots is easier than pulling carrots with square cross sections, okay? Same here. this square cross-section is not very good for flying through air. Although, if you look at the shapes of these transport aircraft from World War II, you should take an interest in that. Some of them had nearly square cross-section, squarish with round corners, but square, probably because that was easier to pack with material, you know, just like these buildings, ugly buildings you see around here. They're all cubical. Cubism was a current in architecture in the early 1900s. Those buildings are beautiful. You see them, for example, on Pennsylvania Avenue, Paris, all these places, but not to be compared with what goes on today. Same here. But so look at aircraft from the Second World War. But in our case, and we're not looking at airplanes when we make this point, which is that the best fuselage cross-section is the one that's roundish, like the cross-section through the dolphin or orca, not through the fish. Ask me at the end of the hour why the cross-section of the fish is not round. Well, the easy answer is because the fish is not a mammal, you know. All right, so that means that the dx is the same as dy, which means that both of them are represented by square root of a. And that's why after the and then something else we do. So this will be substituted in this expression. The point is, let me just put ... Read the PDF. I'm not rewriting the PDF for this occasion, and that means that the front part of equation number 4, this is A plus friction coefficient PL, can be written as d squared and then plus CF, and then the perimeter of the cross section is over D. L is replaced by, from this thing that I erased here, by the body mass, and then over rho of the body to power 1/3. And the PDF says that this expression, meaning the front part of equation number 4, is minimized, or gets to be the smaller and smallest when the aspect ratio is d over L CF over 2, which happens to be a number of 1/10 or smaller. Yeah. So back over the envelope, prediction of how the fuselage should look in profile. Again, think about all the other things that move, you know, birds and then fish and others. They show this universal feature. At the after absorbing this conclusion, equation 4 reduces to, I keep the left of it, which is f over 1/2 rho of air and then v squared, reduces to d squared for A, and then by the way, this scale d squared accounts for both terms at that the bottom of that curve, you know, the Roman 1, Roman 2. This is of the same order as that, so together they are represented by d squared. And then from the right-hand side is TS, and then plus CF SLW. And relying on, anyway, there's more to skip. Next is to minimize the second part. So this is the second contributor to the drag. And that portion, TS plus CF, S, and then W is free to change, but at this stage in the analysis, free to change, subject to fixed profile area, LWT. So subject to fixed LWT. So we're asking the question of how slender should this wing look in cross-section, meaning in a cut parallel to the fuselage. And the answer, again, intersection of asymptotes if you want, is that it turns out that T over L sub W should be of the order of the skin friction coefficient. Skin friction coefficient, you go into the Moody chart, these places. These values of C sub F are of 0.1 or 0.01 in that range the world over. And that means slender. So you expect the wing to be slender. Never mind its shape, slightly curved and all the other features that appeared in drawings for now more than 150 years. So that's what we have. So we're inching toward being able to put everything on this drawing. And then finally, anyway, do you know why the fish cross section is not round? And why the dolphin cross section is round? Dolphin, orca, manatee, and the whale, of course. The whale. And the land-based relative of the whale is which one? One of those did not go into the ocean, stayed on land, spent a lot of time in the river. The hippo, yeah. The water horse in the Greek. These are the same DNA, what I just told you. And the reason is that they are warm-blooded. And the body cross-section that leaks the least heat is the round cross-section when the volume is fixed. That is not the problem for the fish. The fish is not leaking heat. The fish has to be with a vertical oval cross-section because the whole body of the fish is paddling, moving in a horizontal plane. And that's why the tail of the fish is aligned with the vertical, like the rudder on any ship. Well, the warm-blooded animal, in addition to the round cross-section, which is obviously different than the vertical oval, the flipper, the tail, is moving in a vertical plane. Why? Because the land animal that migrated in the water was going up and down on land and kept doing that in the water. Watch at the Olympics, the breaststroke swimmer is doing the same thing, up and down, up and down. And the legs of the swimmer are just like the rear end of the dolphin. They're together and they're doing this. Meaning, if the swimmer is well trained, with a good coach. And this is the biggest hand waving of the sequence. With all these discoveries, equation number 4 that I erased reduces to 2 terms, meaning F over that group is the same as d squared, accounting for the first part of that long expression, and CF SLW. And obviously, you have a competition between, in a group of two, like the two boxers in a ring. At this stage, you rely on earlier discoveries called equations 6, 7, and 11. I forgot to label equation 11, which was right here. Equation 11 was the discovery that T over LW should be smaller than 1. So all these things combined lead to 3 equations called one for the wingspan, equation 13, one for the sweat length, that's equation 14, and then finally the one for the aspect ratio, for the ratio of wingspan to fuselage length, which is, and this one I'm going to write completely. It turns out to be, go through this exercise, just write it fully, m to 1/6, and then gravitational acceleration to 1/2, density of body to 1/3, this SMA, if you want, I call this sigma in the paper, SMA to power 1/4, and then the group rho A, V squared, lift coefficient to power minus 3/4, and then 2 to power 1/4, and then friction coefficient to power 7/6. Complicated, but the question is simple. How does this aspect ratio, meaning the pencil in your hand with which you make the drawing, how does it depend on the size of the object, called capital M? And then you say, gee, well, it varies in proportion with m to power 1/6. And the other place where the body size has an effect is the speed of the flyer. We know, I didn't go into details, but that relationship, predictive relationship between the economical speed and the body size for birds and insects is also correct for aircraft. These are subsonic, okay, aircraft, commercial aircraft. So that means that the speed, remember, the speed is varies as body mass to 1/6. And that means that from inside here, you have body mass to 1/6 times 2, and then to minus 3/4. Am I right? So m to 1/6 times 2, and then raised to power 3/4. Which means that all these exponents add up to what? 1/6, and then minus that's this one makes 1/3, and then divide by that, it means 1/4. Correct me if I'm wrong, okay? And so clearly you put there's a mistake here, because that's what happens late at night last night. Okay, you put 3, and then you put 2, right, to get 12 here, and that means minus 1/12. In the PDF that I gave you, I got plus 1/12. You do it yourselves, okay, please. but there's a typo somewhere, most likely in the PDF. But it doesn't matter to the argument. It means that an exponent like that means that the variations in the body mass are peanuts compared with what you draw. In other words, S over L is essentially a constant, which is in accord with observations of everything that flies, airplanes and birds and insects.